guess it's time. So let's start our webinar. The webinar Bit by Blazing Bit, High-Speed Data Acquisition and Control. Again, good morning and welcome to the webinar. My name is Theo Tiemann. I'm your moderator of today and a program manager of Technolution Advanced and hosting this meeting or this webinar. I'm very pleased to introduce Frank Ambrosius and Gerard Rauwerda, who are today's presenters. During the presentation, you have the opportunity to ask questions. Please submit them in the questions pane, as you can see here, and we will address them maybe during the meeting. That depends a little bit on how many questions, and we will address them at the end of the meeting. Yeah, maybe you can go to the next slide. Thank you. Well, this is Frank Ambrosius. He holds a Master of Science degree in Electrical Engineering, and he is an electronics architect at Technolution. Frank contributes to many projects for Technolution Advanced, and that also includes high-speed data and acquisition systems. And you will hear more about that soon. Please to the next slide. This is the other speaker, Gerard Rauwerda. He holds a PhD in computer sciences and a Master of Science degree in electrical engineering. He works as a business developer at Technolution. Gerard is part of Technolution Advanced, and his main focus is on science and space, the science and space markets. Gerard, you will start with an introduction of Technolution, so please go ahead.
Thank you, Theo. So first I will introduce Technolution, what we will do, and then also introduce Frank into the topic. So Technolution is already in business since 1987, and we are a technology integrator who creates high-end solutions that add value to customers' products. Today we are with a team of about 220 colleagues who all have a passion about technology and work on innovative products, develop innovative systems and technologies for a wide range of clients. So we apply our broad knowledge on, for instance, high-speed electronics, which is this webinar about, but also programmable logic, FPGAs, and software in our solutions. Although we are a fully Dutch company, we also have operations apart from the Netherlands, in Denmark and Sweden, the United Kingdom, and the United States. So I will highlight a couple of examples of what we'll do. We are, as I already told, we are active in multiple market domains where we apply our electronics, programmable logic, and software expertise. For instance, for Technolution Advanced, we build high-speed data acquisition and control systems for semiconductor and life sciences equipment. And in this webinar, we will use a case of a life sciences equipment. But we also build state-of-the-art security solutions and preventive high assurance for classified data, which is done under the brand Technolution Prime. And then with Technolution Perform, we build innovative solutions for industrial machines, such as robotization and artificial intelligence, computer vision. Next slide, please. So today, what will we talk about? We talk about how to design and how to build high-speed and high-throughput data acquisition systems. We will show you how we develop the high-speed acquisition and control electronics for an innovative, fast multi-beam electron microscope, which is used for life sciences, for instance, for brain diagnosis. And we will show you that good systems engineering is essential to understand what functionality should be implemented. And once the right functions are known, then the how to implement becomes important. So where certainly during the product phase, also customization becomes dominant, and therefore we present a modular electronics design which is based on commercial off-the-shelf components, modified off-the-shelf, but also custom hardware that can actually be applied for several metrology systems. Next slide, please. As already told, we apply our embedded electronics and software expertise to build, for instance, data processing and control systems for high-tech instruments for our customers. I rather like to call them partners instead of customers. And in general, these instruments are composed of, as you can see at the left, sensors and actuators, which are integrated by real-time onboard control. And then at the outside of the instrument, it generally involves an additional layer of non-real-time machine control, which you will see at the right as the system control and data processing part. And then, of course, there's the post-processing of the data in order to transfer the data into useful information. And of course, this information may also be spread to the rest of the world, which might, of course, involve also security-related topics. And this general outline of high-tech instruments also applies for electron microscopes, as well as to other metrology systems. Next slide, please. So now Frank will show you how the essentials of designing and building control electronics to implement a robust, high-speed data acquisition system. And for an electron microscope, Frank will also show that the quality of the captured data is heavily influenced by the right synchronization between sensors, actuators, and real-time control. So Frank, the floor is yours. Let's continue.
Yeah, thank you, Gerard. As a use case example of the machine of a machine where sensors and actuators have to operate in close harmony, we would like to present the fast EM, an electron microscope development that accelerates the scanning of for instance, brain tissue samples by about 100 times, heavily reducing research time. And it does that by, instead of using just one single electron beam, it actually uses 64 beams in parallel to image the sample. Technolution has developed this machine not by itself, but with three other partners. The TU Delft, who originally developed the multi-beam source, so the source that ignites not one but multiple electron beams. Delmic is the machine integrator and the developer of the stage, the moving stage with sample, light optics, and also they are in control of the complete workflow in software. And Thermo Fisher is the supplier of the catalog electron microscope. The microscope is actually a modified version of a catalog microscope from Thermo Fisher. And they also did the modification with the multi-beam source, so that is further developed by Thermo Fisher. And as Technolution, we have developed the optical detection and data acquisition system, and combined that with the deflection controls of the electrons. In the next few minutes, I would like to focus on that combination of beam deflection and image acquisition, because if you do that right, the resulting process will look like this. So 64 beams emitted from an electron microscope going through an aperture lens with 64 holes, and these beams are then scanned over the sample in a square grid, so that each beam illuminates a small part of the sample, and that results in a complete image of the tissue. So let's have a quick look in the complexity of the electron microscope. On the left-hand side, you see the actual electron microscope itself. So with the electron gun, the beams fall through lenses onto the sample, and the scintillator, which converts the electrons into photons. And that light is then coupled out of the system, out of the vacuum actually, onto an image sensor. And that image sensor, the data from that image sensor is then sampled and processed First, there are some samples taken together, so we do oversampling there, and we also apply gain and offset corrections on that data set. And that same control system that controls the capturing and also the sampling of the data also generates the scan pattern, so the actual control of the beam deflection. And that creates a synchronous movement of the 64 beams shown in the previous slides. And especially special attention needs to be paid to that deflection of the beams, because you want that to be exactly synchronous to the sampling of the sensor. And after processing of the data, the data is then exported off the acquisition and scan engine platform onto a server platform where two things happen. One is some further processing, and the other one is storage. And with the expertise of Technolution, we developed the data acquisition and scan engine as well as that scalable storage solution. So before we dive into the actual hardware we have developed, I would like to point out a few key figures. The synchronization of that sensor sampling and the control of the actuators has to be very accurate, as said. And a sample is taken of all 64 channels at the same time every 25 nanoseconds, and that is also the time resolution in which the actuators are controlled. So we employ 64 sensor channels and a number of actuator outputs that can be either digital or analog. So onto the actual electronics that we have developed. If you take the hood of the electron microscope, you will see the outlined part on the right. That is developed by Technolution. Of that part, the left side, the left box here is the sensor box. The sensor electronics are in there, and on the right side you will have the acquisition and the acquisition system, and also the control of the deflection. So for the development of the electronics, we took a modular approach, and we did that for two main reasons. First of all, we wanted to create a reusable platform for other products as well. So this will give access to a customizable high-speed analog data acquisition platform, both for external partners as well as for internal product development. And this approach also gave us the advantage to be agile in the development of this product in itself, because not every detail of the final product was known at the start of the development. And by using modules for the edges of the system, we would be able to easily adapt to changing requirements. One of these changes I will highlight in a minute. And these changes hold true for the short term, so during development, but also for the longer term when experiments in the field with first real end users will yield for improvements. So then we can update some of the modules without having to redevelop the entire set of electronics. That modular solution has one basis, and that is a carrier board with the ADCs on it, and also just the system power. And we've added 6 separate modules. We've got the analog amplifiers on the left with amplification and filtering for all 64 channels. And then we have 2 sets of scan control, 2 digital and 2 analog channels each, and these can be interchanged. Actually, only the connector at the outside is different, but the interface is at the inside is the same. And the sensor power supply. We added that as well because this sensor actually needs 72 volts power supply to be able to operate. And of course, we also had the image sensor separate as a module. This enables, by not heavily integrating it into the complete system, this enables us to change sensors in the future if we would, if there would be a need for that. And to also be agile, not only in the hardware development but also in the amount of processing, we have also added the processing platform as a common off-the-shelf system-on-chip module, so that we can upgrade that if needed. Currently, we're using an Intel Area 10 as a SoC module, but in the same form factor with exactly the same pinout. There's also variants in different FPGA brands, but also in cell sizes. I promised I would get back to actually showing you one example of things that we changed during the development, and that is actually in the scan controls. Originally, there would be 4 analog channels to scan control outputs, and in the end, due to some physical constraints, there were changes in control of a part of the system, and that resulted in selecting different hardware that required not analog but digital control. And so that's one thing we actually changed during development. So to summarize, these modules combined in a highly scalable platform for many types of data acquisition in combination with actuator control, especially where it's where these need to be well synchronized. And to get there, as Gerard already mentioned, we needed a well-orchestrated systems engineering approach where the functional decomposition of both the fast EM as well as predicted future products led to that modular approach. And so yeah, the functional decomposition led to the insight that into what functions we were able to buy off the shelf and what custom hardware needed to be developed. So I would like to give the word to Theo again.
Yeah, thank you, Frank. Very informative. I would like to make you aware of other related webinars related to this topic. That's the best system engineering practices for multi-partner high-tech development. This webinar is already given and recorded, and you will get a link to that webinar in the follow-up email you will receive afterwards. And coming soon, we will have high-speed electronics, which focuses on signal and power integrity analysis. And also, if you have systems like this, you have also a lot of data storage, and you definitely need a certain way to do that. So data storage solutions is also a topic we are addressing in the near future. If you're interested, you can follow us through Technolution Advanced on LinkedIn, and you will get more information. It's now time to address questions, and please invite people present. If you have a question, please put them into the question pane so that Gerard or Frank can answer the questions for you. So let's address the questions. Let me see. The modular approach you've shown us, Frank, gives us scalability, but is it also possible that boxes can be combined to even larger systems as well?
Yeah, that's one of the things that we took into account while developing. It's quite easy actually to connect these boxes. There's a few synchronization channels available for that. Yeah. So this box actually gives you access to 64 channels or less, and if you want to go above that, then you need one more box. Yep.
Yeah, so you have scalability in the modular approach, but also in the boxes itself.
Exactly.
Another question, apparently there is no separate board for ADCs present in the box. ADCs are a quite critical part of the system. Why are they not on scalable boards as well?
The main reason we put them on the carrier board is that there was already quite a number of high-speed interconnects on the board. We didn't want to add another set of high-speed interconnects. So connecting the ADC to the FPGA module already has the module connector. And since there is a few gigabits per second going over that interface, we did not want to add another step in there.
Yeah, that
the
sounds
main
logical.
reason. Yeah.
Yeah. I do not see any other questions popping up. So I think we can conclude our webinar of today. Frank and Gerard, many thanks for for the interesting and informative presentation. And I also would like to thank the participants for sharing their time with us. If you have any questions still popping up in your mind later on, you can you go to the next slide, please?
Yep.
You can contact Frank or Gerard separately. Their details are presented right now. And well, I invite you to ask them your questions after the meeting if needed. Well, thank you very much for your attention, and hopefully we'll see you in one of our next webinars in the future. Bye-bye.